Welcome to my Texas workshop. I'm Randy Lammers.
I'm Aaron Keevan.
This is worth knowing. So today's episode is about thread rolling screws. Aaron, we want to take a look at how we take a screw and have it roll its own threads.
Sounds pretty awesome. Let's go.
Okay, so conventional methods that we see out there all the time still today, and it's kind of our low-hanging fruit for cost savings, which is to drill a hole or form a hole and then use a tap and tap that internal threads.
Yeah, and that can be pretty cumbersome and time-consuming.
And costly.
Yep.
And it gives you about a 40% thread engagement. Now, the other thing, Aaron, you've done is then your grain structure of your steel, you've cut the grain structure of the steel.
Right.
So, along the line, people said, okay, how can I save on that? Let's do this. Let's take the screw and make it be the cutting tap.
Sure.
So we came up then with forms of thread cutting screws. And what the manufacturer does is they make the screw with a slight point on it, and then they take and saw out a segment of that screw so that when it goes into the hole of the metal, it actually cuts its way in. And it forms a pretty good thread. Now, it takes a lot of torque.
Sure, and I'd imagine it leaves a lot of material.
Yeah. Yeah, Uncle Mo wants to get his cheater bar out again.
Yeah.
So it does do that. And you have chips to contend with. Think about that.
Yep, for sure.
Electronics industry? No. Can't have metal chips in the electronics industry. So eventually we end up with what we call a thread rolling screw. Now what's really cool about the thread rolling screw is that as this screw goes in, it actually cold flows that metal and allows the metal then to flow around the threads of the screw, and you end up with well-made internal threads. Now you have about an 80% thread engagement.
Right. And you're getting a work hardening aspect in that too. So as it forms that thread, it's actually hardening the material around it as it forms the grain flow.
It does, yeah. So your grain flow your grain structure is maintained and it's compacted a little bit, which creates a harder internal thread. So lots of advantages to thread rolling screws. Now, there are different designs that came out on the marketplace, but the primary one that came out that a lot of people know the brand name of is Taptite.
Right, made by Remick.
Remick Research Manufacturing Incorporated. And so the original patent on the Taptite thread, of course, is up and it's now become a generic part known as a Type TT.
Type TT, seen it in ASME.
Yes, ASME calls it a Type TT, and so does SAE. I want to say this real quick, that Remick has gone forward and has made changes to the patent and extreme improvements on this thread. We'll talk briefly about that later on, but right now let's talk about the generic part that is prevalent in industry today, which is the Type TT thread rolling screw. It is a trilobular or triroundular shape, so basically think of it as being a triangle. And as those points of the triangle go by, it pushes against the side walls, and then the flats come in and the material relieves itself. And when it does that, that metal cold flows and forms an internal thread. It's so good you can come back and put a machine screw in its place.
Right.
That's pretty cool.
That's pretty cool. And we should be able to show that today. I think that's going to be really cool when we get into our demo time.
Absolutely. Now, this is all covered under ASME and SAE?
Yeah, there's performance data for a lot of this stuff. So we're talking about ASME 18.6.3, SAE J81, and DIN 7500. So that covers that metric side.
Exactly. So unlike most fasteners that we deal with that have mechanical properties in it, thread rolling screws have true performance because they have to perform. They have to roll these threads. And so these specifications wrote performance criteria that the manufacturers have to meet when they do that. Let's take a look at one, for example. Let's just use a 1/4 inch diameter as an example.
I've got my chart right out here. So I got SAE J81.
Okay.
1/4 inch. What do you want to know?
Okay, so for what torque do I have to perform to meet a clamp load? What's my clamp load? What's my torque?
Okay, clamp load, you're at 1,600 pounds is where you need to target.
Okay.
And the clamp load torque for zinc-plated screw is 144 inch-pounds.
And that would be maximum.
That's a maximum, yes, sir.
So what that means then is when the manufacturer makes these parts, they have to run these tests. And if that screw will not screw into the as designated hole size for the test, if it won't go in there and form those threads and create that clamp load within that maximum torque, then they've not made a proper part. And that's
hole
critical.
size is critical too. So when we think about the design aspects of that, where should we be at as far as hole size?
Okay, so thank you for asking that question, because hole size is critical. And we actually tell every customer, please test your application, test your metal to make sure the hole size works. But I'll give you a starting point. The starting point is about 80% of thread engagement. So when you look at the chart within these specifications and look at the 80 percentile range, that's your starting point to start your test with. Now, what's really cool is that these screws can be used in just through punched or drilled holes, and they can be used in castings.
Sure. And extruded holes is another one that I was thinking of. So really thin material. We got to figure out how do we make this thing clamp together, and extruding holes is the best way to go, and the thread rolling screw
exactly.
is perfect for that application.
If your steel, if your material is sheet metal is too thin, you extrude that hole down and then let the screw form threads in that extrusion. So there's good criteria written as to what the design of that is, as well as what the design of the casting hole as well, the screw balls. So with that, why don't we start off by demonstrating some of this? We've got a good casting behind us here. Let me grab that and let's do a casting first.
Sure thing, Randy. I'm gonna move out of the way.
Very good. All right, let's take a look at this. We have, looking at we're going to use a 1/4 inch hole, and what you'll notice here is we have pin gauged all of these holes. One of our great customers was kind enough to let us have this piece of casting in order to do our demonstration today. And so we pin gauged all of this. We know exactly what our hole is. Now, I will say this, we're going to use a 1/4 inch, and it does say to make your hole about 0.235. This manufacturer, when they made this casting, they made them a little bit slightly larger, and that's okay, because as we say, test your application. Test what you're wanting to do in your application.
Is it gonna work?
Yep, so let's do that.
Before we get started too, make sure you gotta
our
get
safety glasses.
PPE going here.
Absolutely. So let's go over to our Würth bin, which is, by the way, we do have a patent on this, and pull out one of our 1/4 inch thread rolling screws. So this is a phosphate and oil thread rolling screw. And here, Aaron, we want to demonstrate the fact that this can be done by hand. It doesn't take that much torque. So we're not having to have special tools all the time. You can really, truly do this by hand. Take and put that in. It's going to take you a little bit, but you can do it by hand.
Yeah, that's awesome.
And you can feel it rolling threads. Now, can you feel that triangle shape go by?
A little bit. Yeah, if I turn a little slower, you can definitely feel
that triangle shape go by. And that's rolling that threads in that aluminum casting. So that's how that operates. Go ahead and take that all the way on down.
Sure.
And again, just showing that
Couldn't get me a drill, Randy?
We can do this by hand. No, you can do it by hand. You're a strong man. Okay, now you'll notice, I just noticed it in your hands. Once those threads start forming, then your driving torque lowers. So what we have here is first we have a peak on your drive torque, and then as you roll those threads, your drive torque will then go down. Now, what's really, really cool is you can take this screw back out. Now, when you remove that screw, what I want you to do, Aaron, is pay attention to the fact what we have now is we have what we call a prevailing torque. In order for that screw to back out, it has to also overcome those high points on the trilobular shape. And so that resists vibratory backout, equivalent to the IFI 124, 125 specifications for putting locking elements on screws.
Wow, that's awesome, man.
Okay, so now do this. This is really cool. Watch this. Let me just reach over here. This is a hex head cap screw. So just regular machine screw thread. Look at this. You just made that internal thread. You now give me a component that is internally threaded. And look, I can then put this screw right in those threads.
Amazing.
It is that good of an internal thread. So should your product get out in the field, it needs to be maintained. They don't have that thread rolling screw anymore. Now, we get asked this question all the time. Watch this, Aaron. Give me that thread rolling screw again you just took out.
Got it.
Put that back in there.
All right.
You can put the thread rolling screw back in its place. So you can take thread rolling screws out and you can put them back in. So they do have reusability.
But you do need to be careful with, definitely feel some resistance here. So
Yes.
I'm guessing what's happening here is we're getting some cross-threading. We have to be very.
No, it's not cross-threading. I'm
Okay.
glad you asked that question because that's very common because people think this is what happened. Oh my gosh, that machine screw went in there just like with my fingers. Now this won't go in with my fingers anymore. Why? Because you've got the high sides, you got those lobing, that lobing again creating that resistance. So you continue to get that vibratory resistance, resistance to vibratory back out is what I'm trying to say.
Sure.
So it's a beautiful thing. That's in a casting. Now think about this. We have so many customers that will tap these castings. Look at all of these holes in this casting. Now I can take my driver and just go zip, 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 zip from one side, and there's no cross threading, and you drive right in.
Yep.
Manufacturing efficiencies go way up when you do this.
Of course, and that always equals the cost savings. So.
Oh my gosh, yes. Okay, so Aaron, let's try something different. So as Aaron's putting those on, let me tell you about my 1980 screw gun. Boy, this thing has done a lot of work. It's my trusted handy dandy screw gun. Perfect for the job. It's got some torque settings on it.
It's as old as I am.
Here, it's as old. Oh my gosh, Aaron, I believe you're right. Actually, come to think about it, I think it's older than you are. Okay, so what we have here is we have a little metal coupon just for testing demonstration purposes. And let's put that in our aluminum block. So Aaron, if you will hold that real good with your gloves on there.
Sure can.
And what I will do is we'll get the screws started. And what I want to talk about is then what we have here, if I had this charted, you would see then a quick rise in torque, and then as the threads are formed, that falls off to a lot lower level. So it's what's known as your drive torque. Then as the head goes down, you end up then with the bearing surfaces in touch with each other, and that's more frictional factor, so that's your seating torque. Yep. Now, this is what we get all the time. So hold that real tight. So customers drive it down, they get to their head, they seating torque, and then they do that. What happened there, Aaron?
Well, I think you might have stripped that.
I did. That's called strip out. So that is the common failure mode for thread rolling screws. I can actually take, now that is a loose joint, I can take and turn that easily because that's now been stripped out. So it's the failure mode, and we get this all the time. So what you have to do is you have to test your application in order to find the right torque. So we understand our drive torques, then we start seating the fastener until we get to the failure torque, which is what just happened right there, which is strip out. Now I can actually turn this a little bit by hand. So we have a loose joint. So your ultimate torque you want to use with a thread rolling screw is somewhere about midpoint between drive torque and strip out torque. Now, you want those to be as far apart as they possibly can be, so that's critical to understand as well. So it's understanding those drive torques to the strip out. We need to maintain a 3-to-1 ratio between drive torque and strip out torque. So what we teach customers to do is this. So take your assembly, your metals, your frictional forces, drive your screw, find your drive torque. Then as that goes up, you'll see that torque, you'll see the loads go up, and then you end up with strip out. Identify your strip out. Identify your driving torque, identify your strip out torque, and then your ultimate torque you only use in assembly is about halfway between drive and strip out. And that keeps you from getting there. So that's the way that we want to go with this. So understanding that, let's talk, I guess, a little bit about some of the other issues that customers come with to us about, not only just the strip out torque, but what are some of the other issues?
I've got a list of those things, Randy. So I've got the screw won't start.
Okay, screw won't get started. That happens because you possibly have the wrong hole size. It's so common that customers think, well, if I make it tighter, it's going to be better.
Yeah.
And they end up with the hole size in the 100% category. No, that doesn't work right.
Yeah, and we learned earlier it's really supposed to be about in the 80%.
That is correct. So when the screw won't start, that's the issue. Now, sometimes I will say this, that we do get this from time to time. We get the point of the screw that's not quite right. But the point, this actually has a tapered point. And that point is about 2.5 to 3 threads in taper. Those actually go into the hole. And then you have full thread engagement. So if the point's not right, that'll happen, but it's typically hole size. Okay. Hole size must be right.
Another one that I get is screw won't seat.
Screw won't seat. Screw won't seat is usually a lubrication issue. So the proper lubrication, we talked about this, is wax. So wax is the best lubrication to use.
Dissipates that heat across.
That's right. So heat's your enemy. And if you're driving the screw and you have a lot of heat and if the screw's not properly lubricated, these threads will actually seize up. And you'll actually break the screw in what we call a torsional break.
Right.
So that's the issue. Lubrication's the issue there.
Another one is thread strip off of the screw.
Thread strip out. So, or the thread strip off the screw.
Strip off the screw.
Okay, that's the laser cut issue.
Yeah.
Okay. So laser cut holes. Thick metal today, it's very economical to laser cut those holes. We get that a lot.
Yeah, it's quick, it's efficient, great in manufacturing.
Unfortunately, we have an issue here, and that is the laser cutting will work harden around the hole. And so it'll actually like heat treat that. Not work hardening, but it'll heat treat it. So that's an issue that we have all the time. So we tell customers the screw must be harder than the materials going in. So if you hardened that hole, the screw's not going to go in there. And actually the weakest part's going to give, and that's going to be the threads on the screw. So what you need to do is laser cut your holes small, then use a reamer, ream out that hardening to the final hole size that you want.
Right. It does take away the efficiency, but you're not going to have the problems during installation.
Absolutely, that is correct.
And then obviously we've talked about the thread strip out.
Yeah, so strip out, we just demonstrated that. Again, it's that 3-to-1 ratio between drive torque and strip out torque. We get customers that don't have the proper ratio on that, and they end up with the drive torques too high. Due again to lubrication and hole size. So if you have your drive torque close to your strip out torque, you're going to strip those screws out very easily.
Exactly.
Very common issue. Okay, so in conclusion, Aaron, we have a lot going on here with thread rolling screws. So we have a whole list of things that we want to make sure that everyone in our audience fully understands. So first of all is that we're going to eliminate the cost of tapping holes, and that's a really critical one right there.
Another one is built-in resistance to vibratory loosening. That's a huge aspect and actually will help with that too.
Absolutely. So you can actually get away from some of the thread lockers that are being used.
Lock washers is another one.
Lock washers are another way. So because of the locking capability of the thread rolling screw.
Right.
So also then it generates a stronger mating thread. By work hardening that internal thread, you have a much stronger mating thread, which gives you a stronger joint.
Right. Works in punch, drilled, cored, and extruded holes in many different materials.
Yeah, that's a lot of applications that you can cover with a thread rolling screw. Absolutely. Yep. Cross-threading. That's another one. We see this a lot where a lot of our customers have high production assembly lines where you have a moving assembly line, and the installers end up putting these screws off angle. So cross-thread's a big issue. With thread rolling screws, they can still drive these somewhat off angle.
Yep. Lower installation torque.
Yes. Yeah, so less fatigue of your operators and your assembly lines, and less wear on your tools as well.
We also eliminate plugged holes for paint, for when paint gets in there. A lot of times, spend a lot of money having to mask those things off. You don't even have to worry about that anymore.
That's right. These screws will actually roll right through that paint. They'll just push that paint out of the way, and the paint a lot of times will just help with the lubrication. So that's a big issue as well.
I guess what we're getting to here is we're talking about a lot of cost savings, and I think, Randy, you brought something with you.
I did.
Maybe explain what that is.
Yeah, I wanted to bring this up because I was involved in this. This is a zinc die cast piece, and what the customer was doing was having the die caster actually, after they formed these holes, they were tapping every one of them. We went in and did a full cost study for this customer, and we're able to identify that tapping operation cost them 7 cents a hole. So what they did is they went back to the casting company and said, okay, core these holes at these dimensions, don't worry about the tapping. The casting company was great about that, and reduced the cost of my casting by 7 cents a hole. Now the screw cost more money, but it was nowhere close to 7 cents a hole. Huge cost savings and manufacturing efficiency for this customer.
Right, yeah, and anytime you can improve those efficiencies, obviously you're gonna save that money, so.
Cost savings. So think about this. Eliminate tapping holes. Let the screw do that for you, and roll the internal threads. Thread rolling screws. Manufacturing efficiencies and cost savings. Thread rolling screws. That's worth knowing.
If you like the content you saw today, subscribe, hit the bell icon, and we'll see you next time.